Okay, so let's continue. We're going to do some more moment of inertia stuff. So here we have a uniform rod. Let's say that it is a meter stick, so it's 1 meter long. Okay, and let's say that it has a mass of 60 grams. Okay, or 0.6 kilograms. All right, so anyway, or 0.06 kilograms. Gosh, I think I messed that up earlier. Okay, so find the moment of inertia if the rod is rotated about the end. Okay, well what that means is if we're going to rotate it about this point, instead of the center of mass, we want to find that moment of inertia. And so we say, okay, well it's a uniform rod. We know that the moment of inertia of a uniform rod, right here we can see it, is 1/12 ml squared. But there's a problem. This is for when the axis is through the center. For all of these are when the axis is through the center, okay, the center of mass. And that's really important here. Okay, if we look back to this example, are we rotating about the center? We're not. Okay, which means that while this is the moment of inertia for a uniform rod, it's only going to get us the moment of inertia if we were to rotate about this point. Okay, well, fortunately, there's another tool that we can use here called the parallel axis theorem. Okay, and what that does is it allows us to account for the fact that we're not rotating at the center of mass. And it works like this. Okay, the moment of inertia of something is equal to the moment of inertia about its center of mass plus the mass of the object times however far you are away from the center of mass squared. And this will give you the moment of inertia for any shape based on its moment of inertia about its center of mass and how far you are from that point. So in this case, our center of mass is right here, which means that our value for h is going to be equal to, if this is all 1 meter, it'd be 0.5 meters. Okay, or let's call this entire rod L. That would make this equal to 1/2 L. Okay, so in this case, if we're rotating this rod about its end, its moment of inertia about the center of mass is the 1/12 ml squared. We're going to add to it its total mass times that distance away, 1/2 the length, so 1/2 L squared. Okay, and now that gives us the moment of inertia about this end. Okay, so 1/12 ml squared plus, so we'll square this, giving us 1/4 L squared, so 1/4 ml squared. We can add those together. 1/4 is 3/12. 3/12 plus 1/12 is 4/12, or 1/3, so we get 1/3 ml squared for I. So now this is the moment of inertia if we were to be rotating a meter stick about one end. And you'll see that this is a greater value than we started with because some of the masses are further away from the axis of rotation. Okay, and so that's an example using parallel axis theorem. Make sure you write it down, get it in your notes. This is going to be important for us for the next 2 chapters. Alright, we're going to come back to this example. We saw it in a previous video, okay, where we calculated moment of inertia for this right here. We had 2 masses, okay, and we found the moment of inertia for each and added them together and got 1/2 ml squared. Then we found the moment of inertia for this scenario when we were just rotating it about one end. Okay, we've basically taken this and shifted the axis to here. Okay, which means that if we take this scenario here and use parallel axis theorem, we should end up with the same value for this. Because for this system, the moment of inertia about its center of mass was 1/2 ml squared. Okay, so using parallel axis theorem, it says I about the center of mass plus mh squared gives us the total moment of inertia. Okay, so I about the center of mass was 1/2 ml squared. I will apply the parallel axis theorem for this shift. So the total mass was m plus m, or 2m. Our distance away from the center of mass is 1/2 L. Okay, and we're going to square that. Okay, well, 1/2 L squared is going to give us 1/4 L squared. Okay, 2 times 1/4 just going to give us 1/2 ml squared. Okay, when we add these together, we simplify, and we're going to get ml squared for the moment of inertia if we were to rotate it about this end, which is what we got previously when we did the calculation. And so hopefully this kind of shows you that the parallel axis theorem works. Okay, so we're going to do one more example here. In this case, we've taken a meter stick and we're going to rotate it about it's going to be tied to a 2-meter string that's going to be attached to one end. So we have a string that's 2 meters long. It's attached to a meter stick that's being waved around. Okay, and so we want to find what the moment of inertia of this scenario is. Okay, it's going to be like swinging around, probably pretty dangerous setup here. So anyway, so moment of inertia. So clearly we have a shape here that we recognize, correct? It's a uniform rod, which we know from our table that for a uniform rod it's 1/12 ml squared. Okay, but that's only when it's through the center. So in this example, we have the uniform rod right here, but it's not through the center. So what do we know that we have to do when it's not about the center? Well, that's when we use the parallel axis theorem, so we add to it plus mh squared. Okay, so what we're going to do here, we have to figure out what h is. Okay, well, h is the distance from the axis of rotation to the center of mass, which in this case is this distance of 2 meters plus another 1/2 meter right here. So h then would be equal to about 2.5 meters. Okay, so we get 1/12 times m, and this length here for the rod is 1. Okay, plus m, and h is going to be 2.5. Okay, so we get 1/12 m plus 2.5 squared is going to be 6.25 m. Alright, we're going to simplify that with the calculator. Okay, so anyway, 1/12 m plus 6.25 m going to give us 6.33 times m. Our mass is 0.065 kilograms. If we multiply those, we'll get a total moment of inertia of 0.412 kilogram meters squared. Okay, and so there is another example of the parallel axis theorem.